Welcome mathematicians to this video on finance graphing, where we'll be looking at some of the VCAA or VCAA multi-choice exam questions in recent years. Some of the main features of finance graphs are as follows. First of all, you can look for the general trend, and these are pretty obvious. Are the values decreasing? Is there a downwards direction on the gradient? Are the values increasing over time or use? Is there an upwards trend? Or do they remain the same? Another trend we can look at is the shape. If it's an increasing straight line, we probably have simple interest. A decreasing straight line could be flat rate depreciation or unit cost depreciation, both of which have a nice linear relationship. You could have a curved line. Increasing could be an example of compound interest or an annuity investment, and decreasing could be reduced balance depreciation, reducing balance loans, or annuity payments. And finally, if you have a flat line where there's no variation whatsoever, this could be representing a perpetuity or maybe an interest-only loan. The third comparison feature is that of the difference between terms. If we look at our straight linear graph, we see there's a common difference between each term. For the year 1, it's increased from year 0 by this red margin. Year 2 increases in 1 year the same amount, and 2 to 3, 3 to 4. It's a common difference between successive terms. This equation provides the recurrence relation, which states that the next term can be calculated from the current term by adding or subtracting a common difference. And of course, you've got V0, the initial value. So you can see here there is a common difference between every term. And this equation also below it, it allows you to calculate the future value for the nth term. Moving along, you have your curve graphs. Now these graphs do not have a common difference between each term. You can see it's getting bigger and bigger by the size of the red arrow. These points have a common ratio or multiplication factor between each successive terms, which means if we start here at point 1, we multiply it by a number to get to the value of term 2. Multiply that by the same number to get to the value of term 3, and the same to term 4, etc. So our recurrence relation states that to calculate the next term in the sequence, we take our current term and we multiply it by a factor or a ratio. And of course, we can predict the value of the nth term by taking our initial value and multiplying it by the factor to the power of n, where n is the number of years. And finally, we have no difference at all, whereby each successive term is exactly the same. Comparison 4, change of situation. You'll get these sometimes in exams as well, whereby there's one circumstance and then after a period of time there's another circumstance. So in this example here, which we'll look at in a minute, this has a change of rate. This is a depreciation question where there's a constant value up until the second month, and then there's a new value from this beyond the second month. This scenario here, which we'll look at an example in a second as well, is where we have a constant gradient or a constant rate of depreciation, and then there's a sudden big jump and another continuation of that same rate of depreciation. So let's look at our example. So from VCAA, exam 1 from 2019, question 21. The graph below shows the value in dollars of a compound interest investment after n compounding periods, Vn, the value of n, for a period of 4 compounding periods. So we have our graph, we have our terms, 1, 2, 3, 4, and we have the value Vn. The coordinates of the points where n equals 2, which is here, are 2 and b. We want to know what is the value of b. Okay, so first of all, this may be a long-winded way of doing it, but we know that an arithmetic sequence has a common difference, and that's the generic formula for it. Let's have a look and see if we can find a common difference with these particular points. Common difference would be a straight line. It doesn't look like a straight line just by inspection. But if I compare the difference from value 1 and value 0, I get a difference of 580 take 500 is $80. So there's an $80 difference from the value of this relationship at n equals 0 to n equals 1. But then if I jump up this other end and I compare these two sequential values, V4 and V3, I find the difference now is $124.87. This is not a common difference relationship, so it's not arithmetic recurrence. It must be a geometric recurrence, whereby each term, successive term, is related to the other by multiplying it by a common factor. So from V0 to V1, what we find is if I multiply 500 by R, our growth factor or our ratio, I'll get 580. So I can then divide 580 by 500 to find the R is 1.16. I can then apply this geometric recursion relation to the next two terms to work out the value for V2. I know that I can predict V2 if I know V1 and I multiply it by R, this value of 1.16. Because this geometric sequence, each successive term is related by this multiple of 1.16. So I take the previous term, the 580, I multiply it by 1.16, and that gives me a value V2 of $672.80, which is option C. 2018 VCAA Exam 1, question 20. The graph below shows the value Vn of an asset as it's depreciated over a period of 5 months. Which of the following depreciation situations does this graph best represent? So they've got 5 different scenarios. Now, I want to highlight first of all, each one of these scenarios has some change up after 2 months. So let's consider this in 2 sections. I've got the blue section before the 2-month point, and I've got the yellow section after the 2 months. So let's have a look. Between month 0 and 2, there's definitely a straight line, and between month 2 and 5, there's a straight line relationship. So we know that straight line relationships associated with depreciation come in 2 forms. This could be a flat rate depreciation, or it could be a unit cost depreciation. Although given that it's got here in months, this is probably going to be a flat rate depreciation, not a unit cost depreciation. Let's check our options. Option A says it's a flat rate depreciation, and I'm not even reading the rest of that description. Flat rate is possible, it could be a flat rate. Option B says it's a flat rate depreciation as well, so that's possible. Option C says it's a unit cost depreciation. That could be possible as well. Option D says it's a reducing balance depreciation. A reducing balance would have an obvious curve, not straight line relationship. Option E, reducing balance again depreciation. That would have a curve relationship. So already, without reading the rest of the information, we've got to eliminate 2 of the 5 options because we're not looking at a reducing balance depreciation model. Now the rate of the depreciation is increased after 2 months. So from month 2 to 5, we have a much steeper downhill gradient, which means it's reducing in value more each month than what it was in the first 2 months. Let's now check our other option. Option A said it was a flat rate depreciation with a decrease in depreciation after 2 months. This is not a decrease in depreciation, this is an increase, so that's incorrect. Option B said it's a flat rate depreciation with an increase in depreciation after 2 months. That sounds good. And option C said it's a unit cost depreciation. Well, really this would have units like kilometers or pages or copies or something if it was going to be a unit cost depreciation. It also says with a decrease in units per month after 2 months. So that would be decreasing the rate of depreciation. This is increasing, so that's out as well. So we've been able to eliminate and find that option B was our correct answer. 2017 VCAA Exam 1, question 22. Here we have some kind of value being reduced over years. So this graph could show the value of, and we've got again 5 options. Let's have a look. It's a downwards trend, which means the value is decreasing. Let's start with that as a checkpoint. So option C says a compounding interest investment earning interest. Now if I had an investment earning interest, it would look like this. It would be increasing in value in a curved way, being a compound. This is not a compounding investment. So C is incorrect. D says a perpetuity earning interest at a rate of 6% per annum. We know a perpetuity would have a straight line relationship. This is not the case. So it's not a perpetuity. Option E says it's an annuity investment with additional payments of 6% of the initial investment per annum. So if we were to take 6% of our initial value, 7,000, and add that every year, we would go up in value and it'd be a nice straight line with a common difference. This is clearly not an annuity investment. So we have 2 options available to us. Option A, this represents a piano depreciating at a flat rate of 6% per annum. And option B, a car depreciating with a reducing balance rate of 6% per annum. Some of you will know what the answer is just by looking at the shape of this graph. But let's look at this methodically and see how we go. So we could investigate this to see if it's an arithmetic recursion relation with a common difference. Let's check the difference between 2 terms. So between V0 and V1, $420. Then the next 2 successive terms, V1 and V2, we take 6185.20 from 6580, and there's a difference, a depreciation of $394.80. This is not a common difference, so we can't approach this as an arithmetic recursion relation. So it's not arithmetic. Flat rate is arithmetic. This is what it would look like if it was a flat rate depreciation of 6% per annum. So it's not a flat rate depreciation. So option A we can eliminate. That leaves us with option B, a car depreciating with a reducing balance rate of 6% per annum. This is a geometric recurrence relation, so we're looking for a common ratio between every term. So we compare our V0, our original value, and V1. Put in our terms, substitute them in, and divide the left-hand side by the right-hand side, divide 6580 by 7000. We find R, the factor or ratio, to be 0.94, which means every successive term is only 94% of the previous. So that represents one takeaway 0.94 is 0.06. It's the same as a 6% reduction. And that is in fact what option B talks about, a reducing balance rate of 6% per annum. So a growth factor of 0.94 does in fact represent a reduction of 6%. So option B is correct. And here it is graphically, using the TI Inspire, exactly the same shape. 2016 VCAA Exam 1, question 21. Juanita invests $80,000 in a perpetuity that will provide $4,000 per year to fund a scholarship at a university. The graph that shows the value of this perpetuity over a period of 5 years is. Now, most people will find the perpetuity questions pretty easy. A perpetuity has a flat line or a gradient of 0. Here's a relationship with a straight line. It isn't a flat line or a gradient of 0, so this is not a perpetuity. Option D has a straight line, again with a gradient other than 0, so that's not a perpetuity. And option D, it has a negative constant gradient, again not a flat line or a gradient of 0, so that's not a perpetuity. That leaves us with option A that does have a flat line, yes, and option B that also has a flat line. So it's a case of which one of these is correct. We need more information other than just a perpetuity graph. So this perpetuity had an initial value of $80,000. If we look at graph A, it shows here our initial value at year of 0 is only $4,000. There's 20,000 with 5 divisions, $4,000. So there's not an initial value of $80,000. So option B does start at 80,000 and it does have a straight line flat graph. So option B is our correct answer. 2019 VCAA NHT exam number 1, question 20. Marty has been depreciating the value of his car each year using flat rate depreciation. After 3 years of ownership, the value of the car was halved due to an accident. Marty continued to depreciate the value of his car by the same amount each year after the accident. Which of the following graphs could show the value of Marty's car after n years? Now notice, there's no actual value here, so we're not looking at absolute numbers, but we can try and eliminate as we go. First of all, the value of the car was halved after 3 years. So here's the value of the car after 3 years for each of the 5 graphs. Now in this scenario, after n of 3 years, the value when we go to n of 4 years has in fact dropped to half. So that's holding true. Graph C, we find the value of 3. After 1 extra year from 3 to 4, it drops to only half. Graph D also after 4 years has dropped to half the value it was after 3 years, as has graph E. It has dropped half its value from here on the graph to about halfway after 1 additional year. This graph, on the other hand, graph A, the value of the car isn't halved. You can see clearly half of V3 would be about here, so that one doesn't meet the requirement. So we've eliminated A. It's flat rate depreciation, which means we've got a constant negative gradient. So here's our various gradients. Now this relationship here, this represents no depreciation whatsoever for the first 3 years, a drop in value, then no depreciation after 4 years. So that is not flat rate depreciation. Option C has a constant gradient, a drop in value, and another constant gradient. That holds true. Option D has a constant gradient, a gap, and a constant gradient. Different gradients, nevertheless, but they are still constant. So that is an example of a flat rate depreciation. Graph E clearly has some kind of curve relationship going here. It's probably a reducing balance depreciation. Let's further examine graphs C and D. So we read that the depreciation amount from 0 to 3 years is equal to the depreciation amount from 4 to 6 years. So they should have the same negative gradient. If we look at option C here, we have a constant gradient, a drop in value after 3 years, then it continues on at the same gradient. So this does represent an equal amount of depreciation from 0 to 3 as there is from 4 to 6. However, graph D has a gradient, constant, a drop off in value, and then a different value, a different gradient. Okay, so the rate at which it's depreciating is less after 4 years. So this is not a constant rate of depreciation. So option C is our correct answer. 2018 VCAA NHT Exam 1 Question 20. The value of a photocopier is depreciated using a unit cost method. Which of the following graphs could show the value of the photocopier as it depreciates? Again, there's no values, numerical values, but we should be able to eliminate and find an answer simply by the shape of these graphs. If it's undergoing depreciation, there should be a downwards trend. The value is decreasing. Yes, that's going down. Yes, that's going down. This graph is going up, so that's not good. That is not a decreasing value. This graph is going up, again, not a decreasing value. This graph is remaining constant. This is not a decreasing value. So we're down to two options, A and B. More information. And it says it's via the unit cost depreciation method. Now, a unit cost depreciation will be a constant gradient. So let's examine these two. It's very obvious. Yes, this does have a constant gradient. And no, this does not have a constant gradient. It's changing from a steep gradient to a rather shallow gradient. So we're left with option A as our correct answer. Our final question, 2017 VCAA NHT Exam Number 1, Question 23. The value of a piano is depreciated using the reducing balance method. The graph below shows the value of the piano as it depreciates over a period of 10 years. Let Pn be the value of the piano after n years. A recursion relation that could be used to determine Pn is. Now there's multiple ways of approaching this problem, but let's look at a simple elimination first of all. It does say it's depreciation, and so there's a downwards trend, which means the value must be decreasing. Okay, option A is taking a value and then multiplying it by 0.95, which is a 5% reduction. That would make it decrease. That's possible. Option B is clearly incorrect. That's taking a value and then multiplying it by over 300. That's going to massively increase our relationship. Will not generate this type of graph. So we can eliminate that. Option C is a bit of a tricky one. We're increasing our value by 5% and then taking away 3 units from that value. Now I did my sums, and if our value was $60, if I increase that by 5%, that would make our value be $63. Take 3, that would take us back to $60. But any values greater than 60, this would actually represent an increasing, and our numbers are in the thousands, so we can pretty much rule that one out as well. Option D, let's have a look. Again here, we're reducing it by 5% each time, and we're taking away 342, so that's definitely going to be reducing. That's possible. Option E is we look at the value of a term, and we take away $342. That also will decrease its value. So we've eliminated 2 just by looking at which ones are increasing and which ones are decreasing. Next, which is where we could have started, it clearly states it's a reducing balance method. Now that's a geometric recurrence, which means we're talking about a common ratio between terms. So it's going to be a case of we can predict the next value from the previous value, multiplying it by a value of R, a ratio. Now, if we're going to get it to decrease, R must be a value such as 0.9, 0.95, 0.8, something like that, that's less than 1. It's going to make each term reduce. So this first one, this is taking our current term and multiplying it by a value less than 1, 0.95. That would work, that would reduce, and it's geometric. Option E, this has got a geometric component, but it's also got this common difference component as well, so it's not a straight reducing balance method. And that is reducing the balance by a geometric ratio, but then, in addition, taking more money out. It's not valid. Option E, this is an arithmetic approach whereby we have a value and we take away a common difference to work out the next value. That is not geometric, so that can be eliminated. Which leaves us with option A as our answer. There is, of course, one other way we could do this. This is simply looking at each option and substituting a value for P3 to calculate P4. So first of all, let's have a look at our first option, A. It has an initial value of 8,000, and we can work out the next term by substituting in the previous term and multiplying it by 0.95. So let's put in the value P3 after 3 years. The piano has a value of $6,859. If we multiply that by 0.95, this equation, recurrence relation, will predict the value in the 4th year of the piano to be 651605. And that matches what our graph shows. So this, taking the relationship and actually substituting the value for 3 to predict the value for 4, is another way of identifying the fact that option A is the correct answer. Thank you for watching this video. Using graphical analysis of financial arithmetic is a very good way to test students' knowledge. It comes up on school assessment. It comes up on exams regularly. Each one of those questions was from subsequent exams from 2016. I hope these examples have given you a greater understanding of how to analyze a graph to eliminate and look for common trends within graphical relationship of finance. As always, if you've enjoyed or learnt something from this video, please like, share, comment, and subscribe. And thanks for watching.